Hello. In this short video, I'm going to show you how you can change the mesh of the CFD and of the FSI cases, because what you will want to do is you want to do a mesh sensitivity study or mesh convergence study. That means you don't run a CFD or FSI simulation on a single mesh, because that does not allow you to get an estimate on what the discretization error is. So when we discuss mesh sensitivity, we usually use 3 different meshes, and then we compare the results using those 3 different meshes, and then we do extrapolation and calculate something that is called the grid convergence index, and then you need to report that grid convergence index as an estimated discretization error to show that your mesh resolution is good enough for the case that you are looking at. With experience, obviously, you will get better with respect to guessing the right mesh resolution from the start, but nonetheless, you cannot present a CFD result without doing or without showing that it is no longer mesh sensitive. So you will need to create a mesh that is finer and maybe one that is coarser. This case has 3 different blockMesh dicts, so you could just use those. However, when you read up on how the GCI has to be done, then the ratio of cells in these 3 different blockMeshes is not quite where we need to be. And you may also want to make a coarser mesh, and these 2 other block meshes are refined meshes. So our current mesh has about 20,000 cells, and we want to get one mesh which is about half that and one mesh which is about twice that. So one of these 2 refined meshes is about a bit more than twice that, so that should be one that you can use, but you definitely need to create a coarser one. So let me just play around with this blockMesh dict to show you how that can work. So we will need a text editor to edit the blockMesh dict file. We need a terminal to run the blockMesh command, and then we need ParaView to have a look at how the block mesh looks like. So let me get this started. So initializing OpenFoam. Then the blockMesh command has one command that allows me to write the block format, and that is the option -write VTK. So running blockMesh -write VTK will write the block topology into a format that is the default ParaView format. And so I can simply load that into ParaView. That's in here. And then I can just visualize that block mesh. So you see that there are no rounded corners in this block, and the block mesh is separated into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 19 blocks if I haven't miscounted, and you see the topology of the mesh here. Unfortunately, this does not allow me to give you show the numbers as far as I can tell. If you find a way to do that, please let me know. So you can't get the block numbers and the vertex numbers shown on this, which would help in finding where all of these different vertices are. But this is how our block mesh structure looks like. So let's have a look at what this looks like in the mesh. In this top block, we have a few parameters and variables defined. We have coordinates for the front and the back in Z direction. We have a number of parameters, h1 to h5, for cell numbers. So they are cell numbers, amount of cell in different directions. Horizontal is most of the time horizontal, h, and v is vertical, not all the time, because the block definitions are not always in horizontal and vertical direction. And we have gradients which give us the growth of cells inside a block. But before we discuss that, let's have a look at how a block mesh looks like. So here you see the definition of how the block needs to be defined. So we give in each block, and let me switch back to the editor. In each block down here, we define a block in 8 vertices. So the first block has vertex number 0 to 7. We then have right up here a vertices section where all of these vertices are defined. And they are just defined with 3 coordinates, because a vertex is just a point that is the edge and the node of the block structure. So each vertex has 3 coordinates, and then down here the blocks are made up of 8 vertices. So that's the 8 vertices. They need to be in a specific order, and they need to be in the order of one side, 0, 1, 2, 3. So I always go counterclockwise here. And then the next is the other side of that cube, 4, 5, 6, 7. It doesn't need to be a cube, but a hexagon. And so we have 0, 1. So from 0 to 1 is the first direction. We could call that X. I usually prefer to call that I, as in structure index, I, first index. Then we have 0, 1. Then 1 to 2 is the direction this way. And that is the Y direction, or J direction. So by ordering 0, 1, and 2, you have defined 2 of the directions of the grid. I believe the indexes here in this direction are a little bit out. No, those are faces. So this is phase 1, this is phase 0, this is phase 1, this is phase 2, phase 3, this is phase 4 and phase 5 in X, Y, and Z direction. That's what these mean. So the direction from 0 to 1 is the I direction, or X direction in the block. The direction from vertex 1 to vertex 2 in the order as they are defined in the block definition is the Y direction. And then after we defined the first side of the block, then we go from 0 up, and that will be the starting point of the opposite phase in the Z direction. So from 0 to 4 here, that is the direction that defines the Z direction in my block. So 4, 5, 6, 7, then again, same order as in the first phase. So you define them just as this first phase, just like the other phase. And then you have defined the full block. So the order of the vertices gives you the first 4, one phase, the other 4, the parallel phase, and from 0 to 1 is the first direction, from 1 to 2, the second direction, and from 0 to 4, the third direction. Keep in mind that since this is a C program, we start counting from 0, not from 1. So this is how the block is defined. And then the next 3 numbers in the brackets is the number of cells in X or I direction, the number of cells in Y or J direction, and the number of cells in Z direction. And in Z direction, we always have one cell only. So remember, the order of the block vertices makes the local coordinate system in the block, and then we have X, Y, and Z direction in number of cells. And then we have simple grading, which is one way how you can say what is the relative size of the cells. Simple grading 1, 1, 1 is all the cells the same size in all three directions. The simple grading is only one way how you can define this relative size variation. There are others, and I refer you to the documentation here. 1, 1, 1, all these numbers mean the last cell is the same size as the first cell. If I put a 2 in here, then that means the last cell is 2 times the first one. And that is the definition of all 19 blocks from 0 to 18. And we have these variables that we call in the definition of the vertices. So these $f, $f, $f. Dollar means the following is the variable name, and the $f gets replaced with 0.0 here. $b gets replaced with 0.1. So these are the first 4 vertices on the front. Then we have the back vertices in Z direction. And then the next parts are defining the next blocks. So we have 4 vertices. We have only 4 vertices for the next block because it uses 4 vertices of the previous block. So every block shares 4 vertices with its neighbor. Then we have edges which are not straight. All edges that are straight don't need anything else, but here we have edges that are not straight, and we define simple arcs, and the definition is vertex number, which are the start and the end point of the arc, and one coordinate that is in the middle or somewhere on that arc. And as you know, a circular arc is clearly defined by 3 points: start point, end point, and a third point that is on the arc that gives the curvature. So these make the rounded corners on the cylinder itself, and on the closest blocks to the cylinder, we will see that they are rounded as well. Then the next part is boundary conditions, and here the boundaries are defined by 4 vertices which define faces, and that takes a little bit of drawing the mesh structure on a piece of paper and trying it out. What it is right-hand rule, and you go counterclockwise and count the vertices through, and then the normal vector is according to the right-hand rule pointing outward from the cell. So since we are on the mesh, all the normal vectors that you define that way need to point out from that mesh. So the front has 19 faces, the back has 19 faces, the inlet has only 3. Going here, we have 1, 2, 3, that's the inlet. The outlet has 5. Front and back have all 19. The flap will have 3, and the cylinder will have 1, 2, 3, 4, 5 faces that are defined in that boundary condition definition. Top of the top wall has 4, bottom wall has 4 as well. The flap has 5. There's 2 additional block separations in there. I miscounted here. And the cylinder has 5 as well. The flap has 1, 2, 3, 4, 5 at the end. So it is long. The length of the flap is across these 2 vertices, blocks on top and 2 blocks at the bottom. So that is how this mesh structure looks like. And if I want to change that, then I can simply change the variables here. So let's first run blockMesh now, because I want to see how that mesh looks like. And I then can go in here, and I'm missing the foam file, so I need to create a foam file, cfd3.foam. The touch command again creates an empty text file that we need for ParaView to be able to open the native data. And okay, I need to switch the topology off. I have data already in there, so I need to be very careful what I'm doing here. And I'm not going to continue working on this case because I need to leave the mesh in place as it is. Although I can change the mesh, this one actually, because it is already running on a mesh. But let me switch the surface on, go to solid color, and yeah, that's how the mesh looks like. So you see the block boundaries here are curved, that's one, and you see now the boundaries here are curved boundaries as well. So when I look at this mesh, this looks pretty nice. You see that in this block there's a strong gradation. So from here where the block starts to here, the cells grow in size, and that is what this outlet grading gives you. So the last cell in this outlet block is 11.5 times larger in X direction as than the first cell in that direction, and that is defined down here. This is one of the blocks. You see GO is the ratio for that grading. So if I want to change the mesh size fineness now, I need to simply change these variables. And if I want to change a mesh, so I have about half the cell size, I have a two-dimensional mesh, because I don't change it in Z direction. So I have basically a two-dimensional mesh. So if I want to reduce the mesh size by a factor of 2, then each length needs to be scaled by the square root of 2. So let's say I halve every value. So let me halve this value of 20 and round it to the next value. So either 10 or 11. It's 21 is 10.5. I can't have 10.5 cells, so I need to round to the next integer. If I then save this and go to my terminal, run blockMesh again, that is now not going to work. So let me, oh, no, it should work actually. blockMesh. And I need to reload this, but I need to reload this with the 0 time. Okay, this has broken everything. I need to go back to the 0 time. No, this doesn't work. I can't do that on a running case. Okay, let's make that go backward. So R2 and run blockMesh again. Then I should be able to reload that and get correct values. So since this case is running and has more than one time step, I cannot just replace the mesh. So what I need to do here is I need to copy I need to go into the other case, which hasn't run yet, and play around with that blockMesh. So let me close this one and open this one. System blockMesh ticked. I now change this to 11. this actually may be a good idea because I can now put two block meshes in the same case. So let me open the other case. Again, I don't have the file. So touch mesh.foam. Open that and just look at the mesh now. So this is the mesh. There we are. So this is how the mesh looks now. And what I want to change is these values. So the first block already has changed values, hasn't it? So, but I haven't run the blockMesh yet. So if I run blockMesh again, and you load this, you see now that the first blocks are coarser. Let me do that a bit more extreme and to show you what's happening. So let's just do a quarter of the cells and reload that file after running blockMesh. Don't forget to run blockMesh every time you make a change to the file. You see how there are now 5 cells in this direction, which is obviously too coarse, but it was just to demonstrate what the changes will do. So let's go to 11 again. And that will now create a block mesh that is about half as fine as the previous one. Now I need to change the other directions. Yeah. So let me get back to this. Okay, this front looks reasonable now. And as we said, we want to basically take all of these sizes and divide them by 1.5-ish. So when I do that with the 35, divided by 1.5, then I get 23. So let's take 23 here, save that, and see what happens when I run my block mesh. I get an error because the cell count on one block must coincide with the cell count on the other blocks that it faces. So the faces must have the same cell count when they match between two blocks. So I cannot have 20 cells on this face on this block and 20 cells and 10 cells on this face of this block. So the numbers must match. So in some cases, these variables describe different faces from the blocks, so I need to match those together. So in this case, that seems reasonably straightforward because I have 35 here. So what happens if I change that to 23 as well? Then it works again. So what has changed? Reload that, and I have changed these blocks down here, and I have also changed this edge of these two blocks because this has now changed these two blocks here as well. So if you go through this for all of the numbers, let's just do that for some of them, and then you will get a mesh that is about half as big. So the 78 divided by 1.2 5 is 52. If I do that and run that block mesh again, then I see where that 53 is. That was this direction. So now you see how that gets me a reasonably coarser mesh, and I can work my way through that mesh file and change one and the other, and change them in order. I'm not going to go through all of them now. Amount of cells in radius, let's change that. So 20 over 1.5 is 13. So let's have a look how that looks. Yeah, that's the radial direction here. And yeah, that works out quite nicely. I do get a bit of a change that I don't like here with that growth here. So I may want to change the direction in this sizing here, because that will adjust that spacing. It will also make these a bit more square. And then I can play around with these numbers a little bit to tweak them. And if you need to fine tune this relationship, so this isn't too bad actually, but if you are a stickler for perfection, you might want to fine tune this and play around with these values a bit more. I'll stop the video here to leave you something to do yourself and come up with your own best solution to come up with a decent mesh based on this block mesh dict. But you now see how you can change the block mesh. One thing that is interesting that I want to show you is how these grading factors work. So let me just zoom into this part. So we now, I'm not going to change the numbers, but remember this grading factor here. So when I go back into the text editor and I change that, let's say to a 101, then let's just be a bit silly here, and remesh that and reload that, then this scaling will be much more. Yeah, so it will be ultra fine up at this end and much coarser at the end. So here it's ultra fine, and at the end it's 100 times bigger. So well, don't do that. This doesn't look nice. But yeah, so if you change all of these values accordingly, you will get a good mesh again, which is much coarser. So I have not changed the values in the rear. So I have only reduced it by roughly 4,000 cells by now. But if you consistently roughly divide it by 1.5 or square root of 2, and then play around with these numbers a little bit, then you get a topologically similar mesh to the one that you had, which is just half the cell count. And that is about where you want to be with a coarse mesh. What you can also do, and I'm not sure if a 10,000 cell mesh will actually work already in that way. If you go too coarse, then you will see that the discretization error gets so big that it will start to dampen the oscillation. So the first thing you will most likely see with a coarser mesh is that your amplitude goes down. And that's one of the things you might want to look for with the convergence study. Frequency is relatively benign, but the amplitude gets dampened first. But ultimately, when you go coarser and coarser, you will actually dampen the whole oscillation. So it will stop oscillating for you. So play around with this, and I'm interested to see your results.